before we get into this, though, we need a quick review. We need to review something from 6.2. This was a problem that you were supposed to do back in 6.2. Find the missing side. So, how would you do that? Wait, I found the missing side. Here it is, right here. Sine. You're right. The sine of 42 equals 14 over x.
Or you can use cosecant.
Or you can use cosecant. That would put x on top. That's the one difficulty. Many calculators do not have cosecant, but you can just do 1 over the sine. But let's since we've started this way, let's finish this. How do we, if we're going to use the sine of 42, how do we? I would multiply it by x on both sides. So now we have x times the sine of 42 equals 14. Now divide by the sine of 42. So x is equal to 14 divided by the sine of 42. That's a calculator problem. 42 is not a special angle, nor is any reference angle, so that one has to be a calculator problem. Make sure you're in degree mode. If you mess with the calculator in the ACT to put it in radian mode, change it back into degrees. And mine's in degree mode. 14 divided by sine 42 is equal to 20.9. That's not degrees. 20.9, whatever the unit of measure. Centimeters, feet, miles. So what we're going to be doing a little bit later looks a lot like that, but instead of finding a missing side, the problem we're going to be looking at might look something like this. What if we already knew that the hypotenuse was 20.9, but we had no idea what the measure of the angle was? Hi. You were talking about how you guys are full of crap? Is that what we were talking about?
No.
So if we didn't know the measure of the angle, we would set this problem up similarly, except instead of doing sine of 42, we'd have to do sine of theta. The sine of theta, and a lot of you probably did problems like this last year in Algebra 2. The sine of theta would be what? 14 over 20.9. But the problem is we're solving for theta, and theta is inside of a function. A lot of students would recommend doing this. Well, let's just divide by sine.
Good decision, good decision.
And I know it's tempting. It really is. But you can divide by numbers.
But not functions.
You can't divide by functions. Okay, now over here, it is true that we divided by sine, but what did we divide by? The sine of 42. And that's a number. Sine of 42 is a number. Okay, the sine of nothing, you can't divide by. That would be similar to this argument. What if it were the square root of theta equals 14 over 20.9? Would you divide by a blank square root? No, you would do what? You would square, because squaring is the inverse of the square root. So what we're learning about today is what function undoes the sine function. What function gets rid of it? And it's this inverse sine, and then there's inverse cosine, there's inverse tangent, there's a whole bunch of inverses that we have to talk about. By so doing, we're going to be able to figure out the measure of missing angles. So let's go into inverse. Inverse of the 6 trig functions. Let's talk about sine first of all. So, first of all, does anybody vaguely in their mind, it hasn't been that long, but does anybody remember we talked about back in chapter, I think it was chapter 2, we talked about one-to-one functions. Does that sound vaguely familiar? We better do a quick rundown here of a one-to-one function. You guys all know what this is, right? It's a parabola. It's a function, correct? It's not one-to-one. How come? It doesn't pass the horizontal line test. And the significance of this not being one-to-one is if we were to graph the inverse would look like this. What's the problem with that? It's not a function. So a couple of problems we talked about is we could restrict the domain. Right now, if we just took a look at y equals x squared, the domain is all real numbers from negative infinity to infinity, correct? If we restricted the domain from 0 to infinity, what happens to the parabola? The left side disappears. Now is it one-to-one? It is. So what happens now to the inverse? The bottom disappears, and now is the inverse a function? It is. The reason I'm going over this is the sine, if we were to take a look at this equation, y equals the sine of theta, and this is something, we're kind of skipping ahead, but does anybody remember what the graph looks like from last year? Y equals sine of theta?
It's like a wave.
It starts here and goes up and down, up and down, up and down, and it also goes in other directions. We're going to learn how to graph this more accurately in a couple of weeks. What's the problem with this function? It's not one-to-one. So if we start talking about the inverse sine of a function that's not one-to-one, we're going to end up with a function we're going to end up with an expression that's not a function. So we have to change this so it is one-to-one. That's restricting the domain, much like we did here. We have to change the domain of the sine function. Instead of all real numbers, we have to restrict the domain, and we're going to talk in terms of radians, okay? But in terms of radians, it's from negative pi halves to pi halves. Matter of fact, it's brackets. We include those. So the domain for y equals sine of theta, we restrict negative pi halves to pi halves. For cosine, if we have an equation y equals cosine theta, there's a similar problem. The graph's different for cosine and sine, but they look pretty similar. It goes up and down, up and down, up and down. It's just shifted over 90 degrees. The domain for cosine is from 0 to pi. Now, if you're curious why the domains are restricted differently, here's just a quick explanation. If we considered the sine function from 0 to pi, think about where 0 to pi is. Where is 0 to pi? Which quadrants, I mean? It's quadrants 1 and 2. Isn't the sine the same in quadrant 1 or 2? What if I asked you for the sine of 60 or the sine of 120? Those are both in quadrants 1 and 2. There isn't any difference between those two. The sine of 60 is equal to the sine of 120. We need to have quadrants where the sign would be different. What quadrant is negative pi halves to pi halves? What quadrants are we talking about there? We're talking about quadrants 1 and 4. The sign is positive in quadrant 1, but in quadrant 4 the sign is... What is in quadrant 4? The sign is negative. So if we restrict the domain this way, we have a quadrant where the sign is positive, we have a quadrant where the sign is negative. That's important. Why would we want to restrict the domain of cosine from 0 to pi? It's positive in quadrant 1, but it's negative in quadrant 2. You guys following? So now we have a quadrant where cosine is positive and where cosine is negative. Tangent. Y equals the tangent of theta. We restrict the domain. Now look carefully. It's parenthesis, negative pi halves to pi halves. The tangent isn't actually defined. What is pi halves in degrees? 90, right? Somebody real quick, who's got a calculator? Matt, you type in tangent of 90 and hit enter. It says error. That's why we can't include pi halves or negative pi halves, because the tangent is not defined there. Yeah, it does. So once we've defined and restricted domains of the sine, the cosine, and the tangent, now we can start talking about some inverses.
Wait, do we know why it doesn't work for tangent and 90 degrees?
Yeah?
Why?
Do you have your notes out?
Yeah.
The definition of tangent of an angle was equal to y over, you don't have to. The definition of tangent is y over x, right? We're getting into this, we're kind of getting ahead of ourselves, but do you remember the unit circle? Remember talking about the unit circle? Do you remember talking about the unit circle last year? We're going to learn about this in chapter 5. But anyway, isn't this 90 degrees right up here? What's the coordinate of this point at 90 degrees? 0, comma.
You can't divide by 0.
It's 0, comma 1. Because a unit circle has a radius of 1. This point is 0, comma 1. That means x is 0 and y is 1. Well, if I asked you for the tangent of 90, it would be 1 divided by 0. And what's the problem with that? It just doesn't work. So that's why the tangent of 90 is undefined. Anyway, let's talk about inverse now. Okay, once we have restricted the domains, the inverses are now functions, and that's important. We want to define these inverses as functions. Why do we want to have a function? Well, a function, if you put in one input, what do you get? If it's a function, if you put in one input, you get one output, and that's what we're going for here. We want to have one output. And why would we only want to have one output? Well, think about the problem we were just, I know you're writing, but think about the problem we were just talking about, where we were trying to find the missing angle. If we are going to take inverse sine, but inverse sine wasn't a function, wouldn't it be possible to get a couple of different angles? We wouldn't want that, right? We want to get one angle for theta. That's why it's important that we define inverses to be functions, so that we're sure we're going to get one answer for one input. So let's talk about the inverse functions now. Just of these first three. We'll talk about cosecant, secant, and cotangent in a minute. Inverse trig functions. Let's start with the inverse sine. Ooh. We need to make a table here. Domain. And range. What's the domain of the inverse sine? What's the range of the inverse sine? Well, let's actually talk about the range first. Either look up here or look in your notes. When we defined y equals sine of theta, this is what we set as the domain. The domain is the set of x values, correct? Well, when you find the inverse, what are you switching? X and y. So if this is the set of x values in the original function, if we find the inverse here, then that set of x values now becomes the set of y values. And what is the set of y values? The range. So for the inverse sine, the range is from negative pi halves to pi halves. Now to find the domain, we actually have to consider what the range of the original sine is. This kind of is based on your knowledge of the graph. We haven't really talked about the graph, but I know most of you saw it last year. If we were to graph the sine of theta, it goes up and down, up and down, up and down, but how high and how low does it go? It's the same. Does anybody remember how high and how low it goes? 2 pi was the period for one cycle. And It's okay if you don't remember. It goes as high as 1 and as low as -1. That's as high as it goes. It goes up to 1, it goes down to -1. Up to 1, down to -1. So what's the range of the sine function? If it goes no higher than 1 and no lower than -1, the range, let me write this over here. The range is including -1 to 1, and it's the same range for the cosine. The range for the cosine is from -1 to 1. I don't think we graphed tangent in algebra 2. The range for the tangent is actually all real numbers. So now that we know the ranges, those are the set of y values of the original functions. So if we now talk about the inverses, these set of y values becomes the set of x values. So the domain for the inverse sine is from -1 to 1. Inverse cosine, the domain is from -1 to 1 because that was the range of the original cosine. The range here, what's the range of inverse cosine? The range is from 0 . Now, we're not just making a table that we're never going to look at again or that we're never going to reference. We're going to have to use this table, and you're going to have to recall the information from this table because you're not going to have it in front of you on a test. Why is this so important? Especially the range, you have to remember. If we took an inverse cosine, you are only going to get angles as outputs that are between 0 and pi. Or if we took an inverse sine somewhere, you are only going to get angles between -pi halves and pi halves. That means you're going to get angles in the first and fourth quadrant. If you take an inverse cosine, what kind of angles are you going to get? Angles in the first and second quadrant. Okay, so inverse tangent. What's the domain of the inverse tangent? All real numbers. The range, however, is parenthesis -pi half to pi half. Now, on most of your calculators, this is probably the notation for inverse sine, inverse cosine, inverse tangent. Some textbooks call the inverse sine, instead of sine to the -1, they call that the arc sine. And the inverse cosine would be called arc cosine and arctangent, and so on and so on. Our textbook uses this notation: sine to the -1, cosine to the -1. I mean the exact same thing. But just so you know. Something else before we do some concrete examples. If we were to start evaluating inverse trig expressions, the inverse sine of some unknown value x is equal to theta implies that the sine of theta is equal to x. Now I need you to listen very carefully and try to understand this relationship between inputs and outputs. Let's start with the one that you're more familiar with, the normal trig function here, sine. The input here, theta. Is theta an angle measure or a normal number? Theta is an angle measure. You take the sine of an angle measure, and what's the output? A number. Okay? But this is reversed for inverse trigonometry. Take a look at what the input is. The input for an inverse sine, what's the input here? A number, and what's the output? an angle measure. So when we're taking inverse sine or inverse cosine or inverse tangent for that matter, the output is an angle. If we're taking a normal sine or a normal cosine or a normal tangent, the output is just a ratio of sides of a triangle. It's a normal number, and the input is an angle measure. Keeping that in mind, we have to consider a problem like this. Here's example 1. And the same would be true for inverse cosine equals theta. That implies that the cosine of theta is equal to that unknown value. So evaluate. Part A, what is the inverse sine of the square root of 3 over 2? Now, when we do chapter 5, I know we went out of order, but I thought this one would be a little bit better to start with. When we do chapter 5, we're going to use the unit circle to do this, which is so much faster. Okay? But for right now, we have to kind of use this idea. The inverse sine of the square root of 3 over 2, is that not going to equal some angle, right? That's going to equal some angle that we're not quite sure of right now. This statement implies that the sine of that unknown angle is equal to the square root of 3 over 2. Now, because we're doing this by hand, it's implied that these angles are going to be special angles. 30 degrees, 60 degrees, or they could be in other quadrants, 120, 150. So what you have to think of is, on your special triangles, let me draw both of them here. Here we have the 30, 60, 90. We have 1, 2, square root of 3. Over here we have 1, 1, square root of 2, and this is 45. Of these two special triangles, the sine of what angle would have given us square root of 3 over 2? 60 degrees. The sine of 60 degrees is the square root of 3 over 2. So theta has to equal 60 degrees. Now, it is the convention now to be in radians, because isn't that how we defined this? The domain and range is using radians, negative pi halves to pi halves. So technically 60 degrees would need to be now converted into radians. And it's pi over 3. So the answer is pi thirds. Let's try part B. Inverse cosine, negative 1/2. Now just everybody stop for just a second. Stop for just a second. We defined the inverse cosine to give outputs in quadrant 1 or quadrant 2, correct? That's how we define inverse cosine. Because we're taking the inverse cosine of something that's negative, where is our angle supposed to be? In which quadrant should our angle be? Well, the cosine is negative in 2 or 3, but remember, where did we restrict the cosine to be? Quadrant 1 or quadrant 2. And because we're taking the inverse cosine of a negative value, where do we expect this angle to be? In quadrant 2. Why in quadrant 2? The cosine is negative in quadrant 2. Let's actually do this. The inverse cosine of negative 1/2 equals some angle, correct? That means that the cosine of that angle is equal to negative 1/2. Maybe it's now going to be more clear. Where is the cosine negative? It's negative. Well, it's negative in 2 or 3, but remember how we define cosine. It's from 0 to pi. It's from 0 to pi. That's how we define cosine if we're going to start using inverses. Because the cosine puts out a negative value, where does this angle, where do we expect this angle to be? In quadrant 2. Now, we're going to have to find it still using these special triangles. The cosine of what angle, let's just first talk about positive 1/2. The cosine of what angle would give you positive 1/2? The cosine of what angle would give you positive 1/2? 60 degrees, right? So now you got to think and listen carefully. What angle in the second quadrant has a reference angle of 60? 120. So we're not going to use 60 degrees. We have to go into the second quadrant. And again, why are we going into the second quadrant? Because it's negative. 60 degrees would be the reference angle for 120 degrees. So theta is going to equal 120 degrees. But again, we don't like degrees anymore. We're past that. Degrees is algebra 2 stuff. We're in radians now. So what would that be? 2 pi over 3. So the answer is 2 pi over 3. Let's try part C. What's the inverse sine? Of negative square root of 2 over 2. The inverse sine of negative square root of 2 over 2. Now, that's going to equal some angle measure. That implies that the sine of that angle measure is equal to negative square root of 2 over 2. Now, let's just stop here for a second and talk about this. The sine of an angle spits out a negative number. What quadrant are we in then? How did we define the sine function? Between which two quadrants did we define sine? 1 and 4. We defined sine to be between 1 and 4. But because the sine here takes on a negative value, it's got to be in quadrant 4. The angle that we're searching for here has to be in quadrant 4. Okay? Keep that in mind. Now, this was a little bit of a tricky one. You got to think which one of these special angles, 30 degrees, 60 degrees, or 45, would give you a ratio of square root of 2 over 2.
45.
It's the 45, 45, 90. Why is that? Well, if you took the sine of 45, it would be, the sine of 45 is 1 over the square root of 2, which is square root of 2 over 2. But 45 degrees is in the first quadrant. What would be the corresponding angle in the fourth quadrant? Now, you are correct. 315. Here's the problem with that. If we were to say that theta equals 315, the radian measure for that is 7 pi. The radian measure for that is 7 pi fourths. Does anybody see a problem with that? It's out of the range of inverse sine. If you take a look at this, the range of inverse sine is from negative pi halves to pi halves. So 7 pi fourths is correct. It's just going in the wrong direction. We're going counterclockwise to get 7 pi fourths. We got to go the other direction. It would be negative pi fourths. Negative pi fourths is the same as 7 pi fourths. But we have to use negative pi fourths because that's in the correct range of the inverse sine. Let's do a couple of triangle ones here. All of these are meant to be done by hand, but if it involves a right triangle, those are meant to be done with a calculator. Let's do example 2. Draw some right triangle here. Put an X down at the bottom, representing an unknown angle measure. Some textbooks use an X to represent an unknown angle. Some textbooks use theta. I think our textbook, what does our textbook do? Well, our textbook uses theta, so let's use theta. Sorry, cross it out. Use theta. Now, if the top side here is 4, and the hypotenuse is 9, find the measure of theta. So how is this to be done? Why sine? Opposite over hypotenuse. So sine of theta is equal to 4/9. And now we use inverse. The only way to cancel a sine function is to use its inverse operation, which is inverse sine. Theta equals the inverse sine of 4/9. This is not meant to be done by hand, because this is going to give you an angle that's not a special angle. So it's a calculator problem now. Inverse sine of 4/9. As long as you're in degree mode, this should give you the right answer. Let's round to the nearest 10. So 26.4. Theta equals 26.4 degrees. So just so you know how the homework breaks down, the first entire section of homework, like the first, I don't know, 3 or 4 problems, are like these that we just did, where you do it by hand using the special triangles. The majority of your problems, though, are like this, where you have a right triangle, you need to find a missing angle. Okay? The last section would be like this example here. Example 3. Find all angles between 0 degrees and 180 degrees. That satisfy, there we go. That satisfy the following. Sine of theta equals 1/2. All this section is, if you think about it, is a repeat of the first section that we did up here. It's just in disguise. Find all angles between 0 degrees and 180 degrees that satisfy the following. The sine of some angle has to equal 1/2. Well, that implies that the inverse sine of 1/2 has to equal that angle theta. Correct? Now, since they want the angles to be between 0 degrees and 180 degrees, we can leave this answer in degrees. It doesn't have to be in radians. So, on your calculator, inverse sine 0.5. 30 degrees. What do you think? That's a good question. The calculator is telling us that theta equals 30 degrees. Now the question was, is that the only angle? Because it says find angles between 0 degrees and 180 degrees. What 2 quadrants is that? That's 1 and 2, right? We have to think, though, which function are we doing? The sine of an angle came out with positive 1/2. The key word there is it's positive 1/2. Okay? So if it is between 0 and 180,
So find the first and second one?
isn't there an angle in the second quadrant that would also be positive? You guys follow? Listen carefully. The sine is positive in quadrants 1 and 2, correct? The calculator will only give us one answer because it's using this as a function where one input gives one output. But if we're looking for angles between 0 and 180, the sine is also positive in quadrant 2. So what angle in quadrant 2 would have 30 degrees as its reference angle? 150. So theta also equals 150. Both of those would work. And if you're curious and think, I don't think that's right, type on your calculator. What's the sine of 30? Well, look at that. It's 0.5. What's the sine of 150? What do you expect to find here? 0.5. Both angles would give a value of 1/2. Yep. And in the first and second quadrant, the sign is the same, because the sign is positive in the first and second. So you have a section of homework that's like that. And that's pretty much Let's make sure before we stop. Oh. All right, they're not quite done with it yet. Example 4. Evaluate. This just gets more fun and more fun. Well, before we get too far into this, what would you say if this were the problem? Inverse sine of the sine of pi over 3. What if that's what you were supposed to evaluate? How do we know it's pi over 3? Those cancel, right? What would you say if we did cosine of the inverse cosine of 1/2? What would that one be? That would be 1/2 because cosine and inverse cosine are opposites. Look carefully before you blurt out an answer. Think for just a second before you blurt out an answer. The answer is not 3/2. Domain, think about the domain for inverse sine, you guys, or look in your notes. What's the domain of inverse sine? The domain is from -1 to 1. You can only take the inverse sine of values between -1 and 1. So what's the problem here? 3/2 is 1.5. And if you're wondering, well, no, this is obviously going to work. Try it in a calculator. If you type in sine of the inverse sine of 1.5, doesn't work. There's a domain error. Why does it say domain error? Because it doesn't fit in the domain. 3/2 is not in the domain. This is an impossible problem. Okay, and they will try to trick you with this. Don't just get into the habit of saying, all right, they cross each other out, boom, here we go. Along those same lines, think carefully before you answer this. You ready? Inverse sine of the sine of 2 pi over 3. Think carefully here for a second.
The domain only allows negative pi over 2 to pi over 2.
Did you guys hear that? Does the inverse sine just cancel out the sine function here? And the answer is no. Why does it not happen? It's because the way that we define sine function, in order to use inverse sine, how do we define the sine function? Between which two values do we define sine? -pi/2 to pi/2. Now, that doesn't mean that this isn't going to work. The one above it, this one is definitely not going to work. There's no way we can make that work. There is a way, however, we can make this work. It's called reference angles. What's the reference angle for 2 pi over 3? $60. The reference angle for 2 pi over 3 is 60, or in radians, pi over 3. So guess what the answer to this is? Pi over 3. The answer to that is pi over 3. Why? It's because we have to change 2 pi over 3 into the reference angle that is in the domain, so we change it into pi thirds. Once we change that into pi thirds, now the inverse sine and the sine can cancel each other out, so the answer is pi over 3. So you have to look carefully. You guys following this now? So now consider this problem. That's not even the type of problems you're going to be looking at. What would we say? For a problem like this, let's do the inverse cosine of the sine of pi over 6. Gesundheit. Now, does the inverse cosine cancel out the sine? No, it does not. Suggestions. I'm open to suggestions here. You guys are clever.
The sine of pi over 6 is 30 degrees.
Let's just evaluate the sine of pi over 6. And once we know what the sine of pi over 6 is, then we can evaluate the cosine of that angle. Or the inverse cosine, rather. Now,
Sine of 30. So it's
pi over 6 is 30 degrees. And what's the sine of 30 degrees? It is 0.5, but they're assuming that we're not using calculator, and we shouldn't be. We're supposed to be doing this by hand. So pi over 6 is 30 degrees. How the heck do we do 30 degrees, the sine of 30, by hand? The triangle, the special triangle. So we have it up here somewhere. Here it is. The sine of 30 is 1/2. So we change the sine of pi over 6 into 1/2. So now we're doing the inverse cosine of 1/2. Now, the inverse cosine, hey,
Any luck?
with,
Not finding it?
oh, I haven't really looked. No. Did you, I know it was in your pocket that one day. Did you take it home, maybe?
I did think of it,
Maybe it's at home
but
somewhere.
I brought it back.
Did you?
I swear I put it in there, because I used it just the other day when Megan was trying to help me on. I'll shut up.
Did you put it back in my bag?
I don't think so. I'll look and search.
Okay. Inverse cosine of 1/2 by hand. How do you do that, BJ?
Which one? Sorry?
And we're not supposed to use unicircles yet.
You're not supposed to use it in a circle?
Not yet.
Triangle.
That's what we've been doing.
Anytime you see an arc cosine or an arc sine, you call them inverses.
Yeah.
I call them arcs.
This textbook calls them inverses.
Yeah.
Does yours use arc?
No, I was just always taught arcs.
Oh, alright.
Because the fact that some people believe cosine to the -1 is secant.
That's true. Yeah.
And so it's bad notation.
Yeah.
Anyway, so you draw a triangle, ladies and gentlemen. Triangles.
Like that one?
Yes!
So the cosine of which angle would result in 1/2?
Except in your circle.
We're doing that in the next chapter. 60!
Awesome!
So 60 degrees, but we need to have this in radians. Pi over 3. So that's how those work. Thanks, BJ. Well, have we about had it? There are a couple of application problems.
Are there really?
Yeah. But let's do one real quick. Applications. Holy cow, a 96-foot tree. Where the heck are we?
Redwood.
Has anybody ever seen a 96-foot tree?
I've seen bigger.
Have you? Redwoods? I need to go there. I've never been to the Redwoods. Is it awesome? Ah, I'm going to go. In a year and a half, I'm going to go.
In a year and a
In
half?
a year and a half. My brother's serving a mission up in Northern California, so we're going to go pick him up. Drive through. You know, yeah, but it's southern. You know what my dream is? To rent a motorcycle and drive down the coast, the western coast, and grow a long beard and wear a bandana and just drive my Harley going down the coast.
You're going to have to get that.
That would be awesome. I'll put on like a pregnant suit or something. I don't want to actually get that. A pregnant suit?
Just so that you can look the part.
I want to look the part because you guys want to hear a story? Let me pause this. Back to this. That was a roundabout, wasn't it? So, a 96-foot tree casts a shadow that is 120 feet long. As Mr. Huff passes by on his motorcycle, no, don't write that. I'm gonna get one. My wife keeps saying no, but I'm gonna do it.
So we're going to find the angle that the sun is.
Yep.
Wow.
What is the angle?
Why do I have to be right?
Isn't it hard being right all the time? I feel your pain. I'm always right all the time and it sucks. What is the angle of elevation?
Does your wife ever read about
I hope we don't.
No, but it's okay because she's always wrong. What is the angle of elevation to the sun? So, best way to do this is to draw a picture.
Can you find the time of the day you've got?
Yeah, we need to know that. Here's my 96-foot tree. And it doesn't explicitly say this in the problem, but we have to infer that the tree has a squirrel right about here. So draw a squirrel.
a robot squirrel?
Yeah.
A radioactive robot.
I don't know how you guys didn't read it, but I read it in the problem that there's a squirrel right about there. And then the tree casts a shadow. So the shadow is 120 feet long. And wasn't there a rattlesnake in the problem somewhere? A robotic squirrel?
It's like
A gopher
right
snake?
at the-
A rattlesnake? It was not a rattlesnake. There was some sort of. It was like a cobra and a.
Sounds like the weirdest problem ever.
It was so stupid.
It's like
No.
mission
And it was like,
detectors
there
of
was
the
a
robots.
lot of big words in the space section, and it was like, it got confusing.
The sun is over here,
Some of the science section, there's a whole experiment who did with robot squirrels.
chilling.
Whoa.
Okay?
I've seen everyone post on Twitter, like, giant animals.
So we need to find the angle of elevation.
I've seen everyone post on Twitter, like, about that. How it's that. Yeah, and she's like, oh, she's falling.
What's the angle of elevation? By the way, an angle of elevation is always in reference to a horizontal line going up. That's why it's called an angle of elevation. You never refer to a vertical line. That's why I didn't put the angle theta here.
I like your sign.
Theta here. It's cool, huh? Because he's bright and shiny. Why would he not be?
Because he can.
The reflection out of my bald head, okay?
Well, he's gonna like reflect it off like different objects, like water, outside.
What are we using here? Sine, cosine, or tangent? Tangent of theta is 96 over 120 feet. Inverse. So theta is equal to the inverse tangent, or arctangent.
You can reduce that.
We could. But the calculator doesn't matter one way or the other, whether you reduce it beforehand or afterwards. So we can just type in 96 over 120. Inverse tangent.
I like application problems.
You know how it is. You like application problems?
I like application problems.
Makes more sense.
It's just so interesting.
You've always wondered? Now you can. 38.7 degrees. That's the angle of elevation. What